Hi everyone, in this video we are going to learn how to prove that two statements are logically equivalent with the help of logical equivalence laws, means without using truth table, and in this video we are going to take these four examples. Let's start with the first case. Here we need to show that these two statements are logically equivalent by developing a series of logical equivalence. In the last video, we have discussed the logical equivalence laws, and here we are going to use those logical equivalence law to prove the statements are logically equivalent. As per this question, we need to show that negation of P or negation P and Q, this is logically equivalent to negation P and negation Q. To prove that they are logically equivalent, we will start from its left side, that is negation of P or negation P and Q. In this case, either we can use the distributive law because here it is OR and here we have AND. We can distribute this proposition along with the operator over these two ones. Second approach is we can take negation inside. Now I am taking negation inside. When you take negation inside, we can write negation over the P statement, negation of OR is and then negation over this bracket. In this case, we have distributed negation over the bracket and the name of this law is De Morgan's law. Now we can further take this negation inside this bracket. We have negation of P, negation of AND is or negation of Q. Here we need to keep this bracket because the operator is different in this case. Here it is a and here it is a OR. And in this step we have used again De Morgan's law by distributing negation over this bracket. In the next step we can write this statement as it is, and operator as it is. Negation of negation P is P. In the next case we have operator or, it means we need to keep this bracket as it is as the operator is different. Negation Q as it is. Here we have used double negation law. This is further logically equivalent to what? Now you can check it. Directly we cannot say anything, but we can distribute negation P and over P as well as negation Q because here operators are different. So we can write negation P and P, this OR operator as it is, then negation P and negation Q. Here we have used distributive law. This is logically equivalent to what? Negation P and P, like devil and angel. At a time, both cannot win. It means this is a false statement. And we are operating a particular statement with its negation. Therefore, we are using the negation law. And in the next case, we cannot say anything. So, we will keep the next proposition as it is along with this operator. Now, this statement is further logically equivalent to what? False statement or some statement. So, here we have some statement. We don't know what is the value of this. Maybe true, maybe false. And here we have the false statement. And we are using OR operator in between these two statements. So, this is logically equivalent to negation P or negation Q. Why? If the statement is true, answer is true. If the statement is false, answer is false. So it depends upon the statement. So we are getting the same statement as it is. Basically, it is not losing its identity over the false statement. Hence, we can say that we have used identity law, which is your right hand side. So hence we have proved with the help of developing a series of logical equivalence laws that these two statements are logically equivalent. Next question is, we need to show that this proposition is a tautology by developing a series of logical equivalence. Means we need to show that P implies Q and Q implies R. This implies P implies R logically equivalent to true. For that, we will start from its left side. That is, P implies Q and Q implies R. This further implies to P implies R. Whenever we have the conditional statement, always break this conditional statement into OR form. As we know that P implies Q is logically equivalent to negation of the first statement, that is P. This operator is get converted into OR and this Q statement as it is. Means negation of the first statement, operator is get converted into OR and second statement as it is. We can apply this result in these three cases. In place of this negation P or Q, in place of this negation of the first statement, that is Q, arrows get converted into OR, R is as it is. In place of this we can write negation P or R. The rest of the operators are as it is along with the bracket. So we will put bracket here, here as a bracket. Even in this case we will put bracket, the square bracket as it is, and operator implies. Now again we have the conditional statement. We will break this one again with the help of this logical equivalence law. According to this, we can take the negation of this statement. This operator is get converted into OR and this statement is as it is. In the next step, take this negation and distribute over this bracket, that is negation P or Q, negation of and is OR, then negation of negation Q or R. Now the point is, do we need to keep the square bracket in the next case or not? If the operators are same, we can omit the bracket, but if the operators are different, we need to keep it. In this case, the previous operator is OR and the next operator is again OR. Means we can remove this bracket in this step. Here even we can write negation P or R without bracket because the operators are same. Here we have used the De Morgan's law as we have taken negation over this bracket. So we will put the name of the law, that is by using De Morgan's law. Now again we can distribute negation over this bracket. Even in this case, we have negation of negation P, negation of RS and then negation of Q. Now do we need to keep this bracket? Yes, because here we have the AND operator and the next operator is OR. So we will keep this bracket as it is. So here we write OR, then again distribute negation. In this case we have negation of negation Q, negation of RS get converted into AND, then negation R. Now again we need to keep this bracket because the operators are different and this statement is as it is. So here again we have used De Morgan's law. This is logically equivalent to what? Negation of negation P is P. This AND operator is as it is. Then negation Q as it is. Now again we need to keep the bracket. Next operator is OR. Here we can write negation of negation Q is Q and negation R as it is. Then the statement is as it is. Here we have used double negation law. That is negation of negation P is P and negation of negation Q is Q. This is logically equivalent to what? Now check it. Here we have compound proposition or again compound proposition or single proposition or single proposition. So whenever we have such situation where we are getting the few statements and in between we have the same operator, try to club the statement with same proposition. Like in the first case and in the third case we have P. Whereas in the case second and in fourth we have R proposition. They are liking propositions. As we are following like x square plus 2x plus 3x square plus 4x. What we are doing? We are clubbing these terms as liking terms. Similarly 2x plus 4x because they are called liking terms. So similarly we will take the liking proposition here. Here we need to club this proposition with this one, but before we need to commute these two propositions. So we can write this proposition by this form. Basically, we have commuted these two propositions. In place of this, we have written negation P, and in place of negation P, we have written this proposition. And here we have used commutative law. This is logically equivalent to what? Now you can check it. When you need to club these two propositions, here operators are different. Here we have and here we have or. Even in the case of 3 and 4, here we have and, here we have or. It means we are going to use the distributive law in the next step over these propositions and these propositions. So we can write P or negation P and negation Q or negation P. So we have distributed negation P along with the OR operator over P and negation Q. We need to keep this bracket because the next operator is different. This OR is as it is. Now again apply the distributive law in this case. We write Q or R and negation R or R. So here we have used distributive law. This is logically equivalent to P or negation P. It's like angel win or devil win. So yes, only one will win. So it means the statement is true. And P statement is get operated with its negation one. It means we have used negation law. And in this case, we cannot conclude anything. So we will keep this operator along with this proposition as it is. Also, we need to keep the bracket because here we have and here we have or. Even in this case, we cannot say anything. So we will keep it as it is. Here we put and, so we need to keep the bracket as well. Negation R or R, same devil or angel. So obviously one will win. So this is true because there is a or operator. Again we have used the negation law in this case. This is logically equivalent to what? True and some statement. Whether the statement is true or false or maybe it depends upon the statement. So whenever we have true statement or false statement, you just need to check whether the result is always true, always false, or it depends upon the statement. In this case, true and some statement. If the statement is false, answer is false. If the statement is true, answer is true. It means it depends upon the statement. So we write negation Q or negation P. And here we have used identity law. Also think whether we need to keep this bracket. No, because the next operator is again or. In this case, again some statement and true statement. It depends upon the statement. So we can write this is logically equivalent to what? Now we can write negation Q or negation P or Q or R. Again we will club the liking terms. So we can write negation Q or negation P or R because the operators are same. So here we have used commutative law over these two statements. Now we can club the first two one. So this is logically equivalent to what? Negation Q or Q. That statement is always true, or negation P or R as it is. So here we have used what? That is negation law. Now this is logically equivalent to what? True statement or some statement. So answer is always true because true is dominating the value of this one. If it is false, still answer is true. If it is true, answer is true. So overall we are getting a true statement, and that's what we need to prove. The statement is logically equivalent to true, or we can say that statement is tautology. Next case is show that this compound proposition is tautology by developing a series of logical equivalence. Means without using truth table and using logical equivalence laws, we need to show this is logically equivalent to true. So for that we will take the left side, that is equal to this. So we know that P implies Q. This is logically equivalent to negation of the first statement. This operator is get converted into OR and the conclusion is as it is. So in this case, we take the negation over this statement. This operator is get converted into OR and this compound proposition is as it is. In the next step, we take negation over this bracket. So we write negation of P or Q, negation of and as or, negation over this bracket. Here we have removed the bracket in the next step because the next operator is or. So we write or as it is and this proposition as it is without bracket because the operators are same. Here we have used basically a De Morgan's law because we have distributed negation over the bracket. Now again use the De Morgan's law, distribute negation over this bracket. So we can write negation P, this is get converted into and here we can write negation Q. This operator OR is as it is. Then negation of negation P, negation of OR is and negation R. This OR is as it is, Q as it is, OR as it is, R as it is. Again we have used the De Morgan's law. In the next case, we can simplify this. Negation of negation P is P and the rest of the proposition is as it is. And here we have used double negation law. This is further logically equivalent to what? Now this is similar to the previous case. We have compound proposition or operator, again compound proposition or operator, Q single proposition or again single proposition. Whenever we have such situation, we can observe where we have liking terms because the operators are same in between these sentences. So we can check the first case contain P and Q, in the next P and R, next is only Q, and the next is R. From here, we are going to club Q with the first one and the second with the fourth. It means we need to commute these one. By commuting these two propositions, we are getting this form, and here we have used the commutative law. In the next step, we can use the distribution law, first two propositions and third, fourth propositions. So here we can write negation P or Q. This AND operator is as it is. Negation Q or Q, and we need to keep this bracket because the next operator is different from here. Again, apply the distributive law. We can write P or R and negation R or R. So we have used here as distributive law. This is logically equivalent to what? Here we cannot say anything, so we will keep it as it is. In this case, negation Q or Q, devil or angel. So obviously one will win because it is or. So we can write here it as a true. And in this case, we cannot say anything. Here again we can apply the same concept, angel or devil. So obviously one will win, true, and the rest of things are as it is. And here we have basically used negation law. Now, some statement and true statement, whether this result is always true or false, or it depends upon the statement. So check it. If this is true, answer is true. If this is false, answer is false because we have used AND operator. So it means it depends upon the statement. So we can write this is logically equivalent to negation P or Q. Now we can eliminate the bracket in the next step because next operator is same, that is OR. In this case, statement and true statement, same concept is applicable. So we can write P or R. And here we have used identity as it does not lose its identity over the true statement. Now we can club negation P with P. So we can first commute these two propositions and we can write negation P or P or Q or R by using commutative law, and that is logically equivalent to negation P or P is true or Q or R. Why it is true? Because again angel or devil. So obviously one will win. It means the statement is true. And here we have used the negation law. This is logically equivalent to what? True or some statement. Whether this is always true, always false, or it depends upon the statement. So if this statement is true, answer is true. If this statement is false, answer is still true. So in both the cases, we are getting a true statement. We can say that overall result is true. It means true statement has dominated the value of this proposition, and hence we can say that we have used domination law. So this is what we need to prove. This is logically equivalent to true. The next question is, we need to show that the statement is contradiction, again with the help of logical equivalence. Means we need to prove P implies negation P and negation P implies P is logically equivalent to false. This is the meaning of contradiction. So we will take the left side, that P is implying to the negation P and negation P is implying to the P. So whenever we have such a statement, always remember, break this conditional statement. We can use P implies Q is logically equivalent to not of P. This operator is get converted into OR and Q statement as it is. So we can say in this case negation of P This operator is get converted into or. Second operation is as it is, negation P. As next operator is different, so we will keep this bracket as it is. And negation P, this is already there. We need to take its negation. So we can write negation of negation P. This symbol is get converted into or P statement as it is. This is logically equivalent to negation P or negation P. Obviously, negation P. So that is idempotent law. And in this case, negation of negation P is P. So we need to keep the bracket because next operator is different, or P. And here we have used double negation law. So we have used here as a two laws. One is idempotent and second is the double negation law. This is logically equivalent to negation P, and P or P is again P. So again we have used the idempotent law. This is logically equivalent to what? Negation P and P. So angel as well as devil, both cannot win. So this is the contradiction. Even you can check it from the truth table, or we can say that at a time both statement cannot be true. So this is completely incorrect, means completely false, or we can say that logically equivalent to F, that is false. Hence we have shown that this compound proposition is contradiction. So always remember, whenever we have the conditional statement, first step is break this one into this form, then try to take the negation inside the compound proposition. After that, maybe distributive is applicable, maybe the commutative is applicable, or depends idempotent or identity or the domination law is applicable.